Hello, everyone, and welcome to the show. This is the Geek Nighter podcast, and I am your host, Kaivalya Apte. And today I have Alex with me, founder and CEO of Red Panda Data. And we are going to talk about Red Panda and how it fits into the ecosystem, why it was built, how does it get the amazing performance benefits, how does it get the amazing cost benefits, and hear some of the stories from Alex. So welcome, Alex. I'm really excited to have you here. Let's start with a little bit of introduction about your background, and then we can get started talking about Red Panda.
Yeah, right on. Thank you, Carvalho, for having me. Good to be here. Um, yeah, I guess by means of background, I grew up as an engineer. I guess my you can say my most of my career has been spent as a lead engineer of sorts. I worked at for embedded databases. I worked on a bunch of trading systems. I worked on large scale streaming ingest, worked in an ad tech doing like multi-arm bandit stuff in real time. And so, but I have always personally, I feel like I've always been a storage nerd or an infrastructure nerd. So I've always gravitated towards this kind of problems. Like they were the problems that um, fulfilled me. And so when I was working at an ad tech, I was using a long time ago, and I guess to how we got here with Red Panda, I was working with Apache Storm and Zookeeper and Kafka and Kestrel and RabbitMQ just to do real-time ad bidding and optimization, not the bidding part. And then ended up building a computational engine, also in C++, for low latency. I built that on top of Mesos. I'm not sure there were many other C++ schedulers and oracles built on top of Mesos back then. So we sold that to Akama in 2016, and then I still felt that the problem that I was trying to work on hadn't been really solved on the storage side, and so we had really large clusters. Akama is now a customer, which is great. Large clusters there, and frankly, the computing weren't doing a whole lot of throughput and traffic, and so a lot of the work that came to be Red Panda really started out as an open source RPC framework. If I were to kind of go back and trace, still open. I know in some, I think there was like an Italian database. There's a car manufacturer at some point that was using it for production. And those ideas evolve to become what is now known as Red Panda. So that was the journey. That's how we got here from a technical perspective. I'm still fascinated and energized by continuing to solve problems in this space. It's a very niche space in many ways. I think streaming as a way to understand the world from, I guess, an engineering perspective, I think it's a relatively niche space, but I love it. It's pretty cool. There's a lot of technical challenges to be solved here.
Yeah, I totally agree with that. Um, and probably in future there are going to be more and more interesting use cases coming up for streaming, like when apps are built on real time and not traditional batch systems, because expectations from the users are also more and more real time these days. So um, I'm also excited about this. I want to start with understanding the core problem that you wanted to solve, right? So because I've seen, at least in my experience, whenever I've pitched to let's say rewrite something from scratch, and that too like a system, I don't know, massive system like Kafka, which was mature enough and well adopted. Um, how did you kind of come up with this idea that, okay, let's rewrite a system like Kafka that is compatible with Kafka in C++? What was the problem that was big enough for you to solve and kind of explore this path, which is probably very, very challenging?
It it was born out of, frankly, I mean, you work in reliability engineering, and for those of us that carry pagers that had to SSH into a node, I think there are enough managed services like Red Panda, obviously, that make this a thing of the past mostly. But for those of us that had to, invoking the whatever CK CLI and removing a Z node because that's just like the way you were able to recover a cluster when it was failing at 3 a.m. It really became, I was like, why is it so hard? Why does it feel like systems whack-a-mole to run what, at a high level is a relatively simple concept, right? It's a distributed log largely, like I didn't get it, and then when I was at Akamai, the NOC team, the Network Operations Command Center or something like that, we're operating hundreds of thousands of servers with like 25 people around the world, and I was like, it blew my mind how efficient the operations, and it largely was about building something that was easy to understand and simple. Yesterday I did a live call with the CTO of Jump Trading. They're a market maker, so they're one of the few people that move trillions of dollars in the market. And Alex's point of view, like the single reason why he started using Red Panda was because he could understand it. And then speed was actually a byproduct of trying to build a system that we could reason about. And so, in fact, I think people know us as like whatever the 10x faster version of Kafka, which is true. But really, it wasn't that. That was a byproduct of how we went about building the system. We just wanted to understand where the latency was being spent. Like, where are the clock cycles that are being spent? Can we explain it to ourselves? Like, why is it spending whatever the time in this particular code path? Do we really feel like we have an understanding of where this is? And so I wrote Red Panda originally, really for me, not intending to build a company. In fact, at the beginning, if you go back to the first Git, this is all on GitHub. So if you git clone and you check out the first commit, it was using flat buffers. And so I was using flat buffers, and I sent a couple of patches to the flat buffers compiler for, I think, a custom string type and a custom pointer type. So very like Arrow inspired, super low latency, like think like 26 microseconds round trip tail latency between two computers. And when I went to market with that, no one understood what I was saying from a latency spectrum. I think that application developers just the way a lot of people grew up is not thinking about those details as present when you're engineering systems. I think that there's like this pressure for future velocity of people that forces people to like not care or like defer a lot of the fundamental problems. And so, long story short, it was for me, it was about building a system that I would understand. I was like, how is it, why? Like, why would I choose X or Y or Z? Why are we spending this much CPU cycle on this? Why are we spending this memory on this? Like, how does actually file IO? Why is this so slow? Like, why is this write to the file system taking, I don't know, 10 milliseconds? Like, it's an inordinate amount of computational time. I was like, is the system going out for a smoke? Is there a kernel lock? Like, what's going on? And so I would say that for me, it was about building a system that I understood end to end. And I think to understand a system end to end, you really have to understand its entire latency spectrum. What is the max? And like try to dig into those details to build that. And then that philosophy carried on towards when we started building the clustering mechanisms, where at first, if you check the code out, like some of the early repos had chain replication. And then I was like, okay, who's going to watch the chain? Like, what happens when you replace a node? And then I went and I read all the literature about it. And I was like, look, by the time you end up building a system that can understand how to do proper chain replication recovery, you need an oracle. And the oracle looks a lot like Raft. And I was like, I'm basically re-implementing. And I think people that have built these consistent systems out of pieces come to the same realization that is all a version of Paxos. In many ways, I think, Raft is basically a specialization of a stable leadership of Paxos. And I'm probably not doing a favor here to the original authors, but the gist was like, I just wanted a system that I understood end to end for me. And then it turns out that in practice, it was a single binary. It was really easy to use, and it was really fast, just out of understandability. And then it sort of took off organically, and people then offered us money to start a company, and here we are 6 years later. So that was a long-winded way of how we got started, but it was really all about building a system that I could understand.
Very cool, very cool. And I mean, I gathered a couple of things from that. Like first, of course, the operational overhead, the pain that you have faced, and then the making it really simple, understanding where is the bottleneck, like starting from first principles and solving each problem at a time, and that gives you the side effect of better speed, better performance, and probably also cost effectiveness. One thing I'm very curious about is the Kafka compatibility, and not like why is it Kafka compatible, because I think it's fairly obvious that Kafka is a mature system as a protocol. It's widely used, so why not make it easy for people to kind of move to Red Panda or a system that is compatible to Kafka, right? But what are the challenges associated with that? And more than challenges, like, okay, challenges in terms of keeping it compatible, and it's an ongoing process. But are there any bottlenecks that you have found in the journey of being Kafka compatible?
Yeah, it I think that was about three questions, but let me answer them. I think um, maybe in reverse. Could we implement something better either on latency or throughput perspective if we weren't bounded to the Kafka protocol? 100%. Like there's not an inch of doubt that we can build something that is lower latency. 0% doubt. It's just like, but Kafka, like TCP, it's super useful. I mean, I think that people have proven that you can do better than TCP, but there are just very few companies that are willing to go and do the work of adopting a new protocol. And so, and I think a meta comment, and then we'll talk about compatibility in a second, is when I started the company, it wasn't obvious. I mean, I think it's obvious now. I'd like to, the company, not me, take some credit, I think, for bringing that nuance to the wider discussion. When I started the company, right? I mean, I think that our main competitor was saying, just like from a marketing perspective, the most inane things is like, we are Kafka, but we're also better than Kafka. And I was like, it's like a Schrodinger cat. It's either the cat dead or the cat is alive. If you're Kafka, then you have to be exactly the same as Kafka. Otherwise, you're not Kafka. And then, by the way, we have to compete on a different implementation. And like, I was like, okay, but the market has to make a decision. And so I think before we started, there was confusion around the world that Kafka was like this one thing. And I think what we brought to the market, and is now popularized by a bunch of competitors, that okay, Kafka is many things. It is the community and the code that people have written, and it's probably the most valuable part. Is not github.com/Apache Kafka. I think that is a core pillar. We wouldn't exist without that community, and so like I'm very thankful for that. I think that we expand that community. I think that just like the C++ standard, having two compilers that implement the same API, it's helpful for the world. I think that we've pushed the project in dimensions that maybe they wouldn't have if they had less competitions. And so okay, so I think it was useful to add nuance about Kafka, the protocol, Kafka, the community and lines of code. That is, I think the most valuable part is the tens of millions of lines of code relative to the 400,000 or 500,000 lines of code in the GitHub project that people have written. And so whether you're the largest electric car company or the largest bank or the largest CDN or the largest security company, just to name some examples of our customers, they, being compatible with that matter. And then the third one is, how hard is it to keep compatible? It's less difficult for us than people think. And so when we approached this, I didn't want to have on-disk compatibility with Kafka. And I think that we had learned from other databases that made that mistakes. It's like, hey, you could do this rolling upgrade where you bring one node at a time of this new system, and then you kind of do this replacement. And I was like, that doesn't give me enough space to innovate. In part, we chose a totally different consensus protocol. We chose Raft. I think that the community was forced in or accelerated K-Raft because we existed. And so all of the ideas around replication, like on-wire format, those skips are not applicable to us, right? So there's a very small surface area, which is the public API that consumers and producers interact with. So obviously the transactions protocol, etc. But by not having on-disk compatibility, just public API compatibility, think of it, it's like maybe 25% of the API, something like that. And then secondly, that compatibility layer is largely super mature and stable. And so what we did instead is that we wrote a bunch of parser combinator libraries for C++. And so we take the IDL that the Apache project produces, and we code generate the C++. So no one at Red Panda is sitting like, if this and that, except for a couple of handful of bugs that are like, because there's like two cases that I remember over the last 6 years where we have to like introduce incorrect behavior from a protocol description perspective because the implementation for those versions had a bug that mattered in a meaningful way to clients. But other than that, it's largely, it is a solid implementation. I think it's had some good engineering over time, and largely because it's just been used so widely that it's well tested, it's well understood. And so when it comes to building a compatibility layer, it's relatively quickly. Like from the time that a KIP is finalized, the JSON IDL is committed into the GitHub repo. As long as it's not like a meaningfully complex, it's like days, right? So think of like, I don't know, 3 days to like generate the IDL, port over the test cases, download all of the open source clients, whether you're using like Go or Python or C client or Java client, push it to CI, make sure that we pass all of the unit tests for those things. That's roughly how it is. So it's a lot less complicated because of how we build the infrastructure. And so instead of focusing on building specific parsers, we focus on building a compiler that then compiles the code. And that was some lessons learned that we took from Smurf, the open source project, where we wrote a compiler for flat buffers to generate the C++ code. I was like, hey, we can sort of take the same idea and intuition here and then generate all of the IDL. And then it's just a matter of hooking it into the storage engine. And then, the team that has done a great job about extracting like, whatever, atomic configuration swaps or leadership pinning or like a bunch of like raft mechanics or saving files on disk. And so it's a lot less difficult than people would assume for us. I'm not sure how it would work for others. But I'm going to pause here. Those were the technical decisions. One was like diverting away from the on disk formats, and therefore all of the protocols that came only staying true to the public interface, not the interbroker or zookeeper KIPs or KREF KIPs or anything like that. That's just like, that's internal implementation and people don't care. What they care is you bring an app and you connect to this thing. And, does it work or does it not work? And I guess proof is in the pudding, where we haven't had a single customer change an application, a single line of code, in 6 years with the world's like largest customers and like, both old and new enterprises to date. Maybe it'll happen once, but so far it hasn't happened.
That's really powerful. And I want to get into that a bit more, like from the storage perspective, because I also, read about AutoMQ and did a podcast also with Warp Stream, which takes the state out of the Kafka cluster to object store and how things are simplified. I want to understand your viewpoint. Well, let's start with, since the space, like the stream processing space, Kafka compatible solutions, there are many of those now. What do you think in terms of like the uniqueness of Red Panda, so to say, as compared to other solutions? If you have to pick some, what would they be?
Yeah, I think it's a great idea. So we haven't seen much competition with Red Panda on the low latency space. I think people have understood. So let me break the market into multiple segments so I can give an intelligent answers of how do I think about the world. And so if I look at the dollars being spent on Kafka, I think it's somewhere around $30 billion of market that are being spent on people either spending money or time or on services or something like that, right? And so if you look at the revenue from the top vendors, it is 10x less. If you sum all the vendors, there are 10x more dollars being captured for existing Kafka workloads that are there. And so like I think it is useful to have that context as part of this answer. And so on the operational side, at least to me, I'm not sure if there's a system that that is better than Red Panda. I think if you care about latency, predictability, etc. Jump trading was a great example yesterday, just to mention Alex, mostly because he's like an OBS founder, or excuse me, CTO, and he talked about like the tests that they did, and he talks about real things, like they had some bugs and they crashed when we first tested Red Panda, and I kind of pushed it to the limit. But anyway, so that's one part where I think we are probably the strongest product in the market there. And then there is the diskless option, which is, I know MMQ is slightly different with EBS. And so the way I think about that is that we are obviously working on that, and so is every vendor in the world. And I think similar to vector databases, where at first it was thought of as a different database category. Instead, every database in the world simply added vector database capabilities. I think the same thing will happen with this write-through caches to S3, right? Like it would be, I guess without putting people on the spot, it would be dumb for Amazon not to do it with their implementation, right? It's just like, and it would be, I guess not astute to think that every other person is building that, but where the dollars are being spent today is, if I'm looking at go-to-market, it isn't on the analytics. I think that tends to capture the mind hive of perhaps Hacker News or others. It is true. It is important. Just like vector databases, it becomes like a pillar for how people are continuing to build the future. But when I talk about dollars spent, there's still a larger, like maybe 100x larger pool with the applications that exist today. So the main difference, therefore, between us and other engines is that I wrote a blog post that I called Red Panda 1. It's this idea of having a single engine where instead of thinking about the future in terms of clusters, people will start to think about the future in terms of topics. And that's cool, right? And so that's our hope with our serverless, for example. And so the idea is that on the same cluster, you should be able to have ultra low latency. And so we power some of the largest sporting events in the world. And I think the latency for measuring that was 800 microseconds, which was, it came through like months of tuning the kernel and doing a bunch of things. But like, why couldn't you have mechanically, there's no reason why you wouldn't be able to write to tiered storage as a pass-through and in cluster. We already have the in cluster, and we've been writing to tiered storage for many, many years. I think we probably have one of the most mature implementations of offloading data to tiered storage. So the question is, could Red Panda also write just directly to tiered storage? The answer is obviously yes. And so, we'll be releasing that, but there isn't the financial pressure for us to like deliver that ASAP. I think it'll happen. It'll happen soon, and it will happen with every single Kafka API implementation, right? I think it's an important feature, and just like vector databases, it'll be a path forward so that you can have multiple use cases in the same physical cluster. I don't think my view on it is, I don't think it's like a standalone new form of a streaming. In part because when you actually measure latencies, I don't know which object storage systems people are testing, but it is untrue that it's less than 1 second, right? Like actually, most of the time, we have personally seen latencies in the multiple seconds. It's like 2, 3, 4, 5, 6 seconds or something like that. That's common. That's not like, hey, an anomaly. That's like whatever. You'll see it once every couple of days, and so therefore, like it's a totally separate class of applications. I think the benefit is obviously the cost effectiveness. And so that's why we will also have it relatively quickly. But as a startup, you always have limited resources, so you have to like index where you win and continue to make progress and continue to innovate.
Awesome. And that's a great point, actually. To make it a bit more clearer, like, okay, we get the performance benefits, low latency, but what exactly is done, like apart from writing it in C++, there has to be many optimizations at each layer of Red Panda, right? So if like take us through this journey, like starting from the high level architecture, what is the difference when I am writing data into Red Panda? What exactly is happening, and where is the performance benefit coming from?
Yeah. I like to say that latency is the sum of all your bad decisions, and so um, it starts, I guess, at the lowest level. We use a framework called Systar, which is a structured message passing technology. And so the idea is that every core in a computer, so you divorce concurrency, program structure, from parallelism, which is the simultaneity of the execution. And so you write software in this concurrent software structure, right? And so like it very much feels like an actor framework to people that have written actor code. You send messages to this course very explicitly. And so you say like send message literally, like you take a lambda and then you pass it to core 32 or core 54 or whatever it is. And then you send the message to that. At its lowest level is a n square network of queues based on the number of cores that you have in your system. And so every core has an inbox and an outgoing mailbox for every other actor in the system. And the intention there was to start to optimize the cost of message passing at the CPU level. The next level from that is that we don't use the system allocator. And so we pre-allocate the memory up front. And what it gives you is we onboard the complexity away from the system allocator into the application space, because instead of having bytes, we can have fully materialized objects. And so this technique is super common in high performance computing. We didn't invent it, we just thought, leveraged some of these core ideas. And so an example is when we get a Kafka request, we already have a fully materialized object in the exact sequence of bytes that the client expected. So we can just flood the pipe as fast as possible once it gets into that. And then we can also build in caching mechanics and heuristics that are specific to the Kafka protocol read patterns, right? So we have a cloud and we get to study a bunch of how the standard client behavior is done. And it's like, could we optimize that? And the answer is yes. And so can we embed caching mechanics on that are application level stuff? And then kind of, at the next level, then we optimize the replication protocol. And so instead of you doing the ISR, we did Raft. And I think there was probably a mechanical difference between where the project originally started and where we are with cloud today, which is by and large, clouds are pretty good these days. It wasn't like it was, I don't know, 12 years ago, which it wasn't great. The reliability, at least when I was building a bunch of products myself, of the clouds, it wasn't great. It was fine. It just wasn't as good. And so now these days, networking is amazing on really on all three clouds. I think disks. Some clouds have a slightly better disk than others, but largely clouds are pretty good these days. And so the thought was, can we build a protocol that is best of majority as opposed to worst of chain? And so and so with Raft, we've done a bunch of implementations inspired from CPU prefetching and out of order execution, where it's hard to showcase, I guess, on audio, but where this is the same as this. And so in other words, if you get 3 writes and you have to durably commit 3 writes to disk, just to give intuition to the listeners, technically, according to the protocol, you have to do write flush, write flush, write flush, right? But if you coalesce, if you accept 3 writes, and I'm talking about single digit millisecond debouncing or coalescing, say 3, you could do write, 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 flush, and you've skipped 2 flush operations that could be expensive depending on the media. And so there's a bunch of protocols optimizations really from that end all the way to higher end. And then we've done a bunch of protocol optimization on metadata lookup. Could we do, could we continue to optimize the latency or metadata refresh so that we can have higher partition density, as an example? And so, man, I could talk about performance for a really long time. It's so fun. I guess the last one, which is fun, that we wrote is that on the wire structure. So we wrote our own RPC mechanism. So that is super ergonomic to the engineers writing the storage engine. And so you just write regular C++ code, you do a couple of annotations, and then it like serializes the stuff on wire, relatively high performant. And so for comparison, just like what does this high performance means is faster than flood buffers, right? Which is faster than Arrow in most cases. And so one of the things that we've done there is that we've done custom compression for the heartbeats of Raft. And so what we've learned is that most consumers tend to consume partitions rather evenly if you have a consumer from a particular consumer group. And so if you're sending numbers around, you could do like a delta encoding of the particular offset so that you're sending, bits as opposed to bytes. And so it's really, so it's hard to say. I guess I don't have one trick from the back pocket that I can say, it's like, this is the whatever, this is the red card or the green card, that like this is the reason why. It's really the accumulation of all this little performance optimizations over a long period of time. And so I guess the summary for me would be, we built this culture internally, and I think a lot of it came from the early people that I was able to hire that were just like super good systems engineers that thought about the world in terms of, perhaps how I thought about the world, right? Like clock cycles, how do we continue to optimize? How do we like relay the formats on the wire so that you get all these optimizations? How do I care about the tail latencies? How do I care about predictability and understandability of the systems? And so over the years, it's continued to pay dividends on a performance level. And then, really we could talk more, but I'm going to pause here because that was a lot of technical content. I want to make sure I'm not losing the audience.
No, I think it's a very like amazing insights into each layer, and as you mentioned, it all adds up, and let's say adds up, but reduces the latency, because you have performance optimizations at each layer, because doing it just on one layer isn't enough, and there's always some opportunity, depending on what is the bottleneck. You mentioned about this, the C star framework that you use, and I believe you were pointing to thread per core architecture with that, right? So let's talk a bit more. Like, I understand, like when you have like one thread per core, probably you are reusing the context switch and the overhead of that. What are other advantages of this architecture?
Mentally, for the engineer who is writing code, for those of us that had to work on million line code bases, or maybe even 500,000 line code bases, that over time people add multiple concurrency and parallelism paradigms into the same code base, and it sucks to debug those systems because you don't know. You're like, man, I can't possibly understand the interaction, or it just takes a very long time and a bunch of sequencing to understand the system. And so I would say the thread per core main advantage, and this would be true of really of any paradigm that people adopt and they go all in. In fact, I'll tell you like the drawbacks, because there's some major drawbacks. Largely it comes from re-implementing a bunch of the libraries that have like terrible lock-in semantics. And I was like, why is this thing taking a global lock? Like, stop that. You're polluting my caches. But okay, anyways, so from this like thread per core architecture, like what you get is that once you start executing, you're in a single thread context. You don't have to take as many complicated locks as you would. There's still a lot of complexity around building a storage engine, so I'm not going to try to say that the job is easy. You still have to think about sequencing because you have coroutines and preemption and comparative scheduler inside the thing. Otherwise, it's too slow. So a thread per core architecture on its own is not that interesting. When you add cooperative coroutines, right? And so where every core is actually its own like work scheduling in a cooperative way, which means like as you're doing work, anytime you think you're about to block, you explicitly yield in code. Like you literally write in an instruction that's like yield, because it's very likely that this function is going to block or it's going to take a bunch of time. And so you allow for a core level scheduler to resume a separate coroutine that is ready to be executed in that context. But so the largest win is at least an opinionated and sound concurrency and parallelism model. And so what does that mean in practice? That means that people can embed Red Panda all the way to like moving vehicles in a single core. With Red Panda has been shipped to outer space, by the way, using a fraction of a thread and very, very little memory, because like it scales down to those primitives. But it's also run, like yesterday for jump trading, in like, hundreds of cores on a single computer. And so what you're doing is you're divorcing the simultaneity of execution to a runtime variable, but the engineer at Red Panda is writing code with like one model, which is like, okay, inside one core, it is a single thread context. You have coroutines, but that's sort of like a way to get additional performance. And so is it the best? I mean, I think it's hard to say. I think it's a really good fit for this data intensive applications. I think it's a lot of work. I would not recommend it for people not building systems, right? I think if you're at an application level space, I like Go. I think Go is like the pearl of the 2020s. There's like a little library for just gluing just about everything, and it's like really quick to get everything up and running, or to glue multiple services. Slow, but otherwise it's a pretty great. It's a fantastic language that people can wrap their heads in a week and be super productive. A thread record architecture is not like that. It requires like a pretty big initial lift on how you approach thinking about the world, where like now you can cause a bad system performance if you simply push a global lock, because like everything about the system has this particular assumption. So it's great for systems like Red Panda or databases, or I know that there's like networking proxies. There are like storage appliances that are using this framework successfully at scale. I think Red Hat is building the new storage engine on it too. Super useful. Where I think it is not great is the opposite of Go in that regard, in that Go has all these little great utility libraries to just do everything imaginable. The Systar framework, because it's so opinionated from a memory mechanics perspective and threaded and lock-in, forces the engineer to rewrite a bunch of the code. And so we just wrote integration with Apache Iceberg, for example. And if you look at the code base in GitHub, was like 40,000 lines of new code that we had to write, because there weren't good libraries that were built for Apache Iceberg in C++ that use weird or like replacing types in the type system wasn't easy. And so you would have like implicit global locks, let's say by state string or something along those lines, depending on the compiler implementation. And so those are the downsides from like, I guess, a feature velocity. And then last, the upside is that therefore, because you end up owning your dependencies really well, the dependencies of Red Panda on a library perspective are super small. It's like, I don't know, 12 core libraries or 15 core libraries total. And so we own the system end to end, and it allows us to reason through end to end, whether we're like columnarizing the types and pushing it to an Iceberg catalog, and whatever, parsing the protocol formats and writing it on as a different format, or doing this, we understand the performance end to end. But there's no free lunch. Like, you really have to put in the effort from an engineer perspective to reimplement almost most other utility libraries that you would get for free in other programming languages. So those are some downsides.
Yeah, very, very cool. And thanks for the insight, like giving, good parts, but there are also like challenges and probably negative parts depending on the use case. And that's very interesting. The other point that you mentioned is that you don't use the system allocator. And the one advantage that you mentioned, that you have the objects as it is, and you don't have the you don't have to spend time to kind of convert into the object and convert it back. But does it also gives you some benefits in avoiding memory fragmentation in some way?
Yeah, gosh, what a astute observation. let's dig into memory allocator mechanics because it's fun, and so obviously there's some really smart allocators. I think the library from Microsoft's recently is actually quite good. I think it's called memalloc. Obviously you have jemalloc from Facebook, and the libc library is fine. It is more than just shipping bytes. I think I was just trying to give the listener what I tend to call Hollywood highlights, this like intuitive understanding of why someone would go to the lengths of building your own body allocator. And then, caches and arenas and moving pools, it goes beyond that, and it really results in systems understandability. And so I think I mentioned this before, but there is no way to eliminate essential complexity, right? Like if the job is to save data to disk, that's the job that the system needs to do, and it needs to do it reliably. Accidental complexity are the things that you can eliminate. And depending on the use case, for example, using the page cache could be considered accidental complexity. In fact, there was a bug in Postgres that was live for 25 years, I guess now almost 30 years now, where calling fsync on the page cache actually didn't, in fact, durably persisted the data to disk. And so that's like one example. But to stay in the allocator and not in the file system mechanics, we can reason about throughput and latency and propagate back pressure from how the disk is performing all the way to the TCP connection by owning the memory, right? And so because we don't have a system that is throttling Red Panda, and so in other words, when you call malloc to the system, if the system doesn't have memory, it's going to block the thread. And the programmer is like, they have no clue. They're like, this is great. I can just call malloc and it's true. And largely it works. But when you can't, it'll wait until there's some space, and then it'll give you the memory. And then you sort of continue, you have no idea what happened behind the covers. That is not true with the way that we've built the system. And so you have to build this throttling mechanics. And so what is one place, for example, where this shows up? And so this shows up where a request comes into the networking layer, and we allocate, I think by default is about 30% of that particular L core memory pool mechanics goes to the network, to the networking code. And then you can oversubscribe manually, right? So you can reason about your systems. And so, okay, a request comes in, then you allocate, let's say, a gig for some, it's too much, but whatever. Just say a gig of memory on that particular network request. If you don't have memory units to allocate it, you could do two things. You can tell the client to retry, right? So you can inject an error code from the Kafka client. Sorry, cannot take your request. Please retry. And so that's failing, and therefore you would allow other requests to come in, or you can wait for other systems to free up. And so the balance is somewhere in between, where you accept the right, you hold some units and you're waiting for more units to come out until there's a timeout. I was like, I waited for too long. It is better for the system overall. So it allows you to have this global heuristics to cancel this request, to actually let a bunch of small requests come in, because it's going to lower the memory requirements of this core. So I can, by the time the network retries again, I'm actually going to be able to serve this request, because I am able to serve all of this small requests. And so you can reason about those things explicitly. And now when you're out of memory, you can therefore push latency mechanics either to the IO subsystem or to a networking subsystem. And so there are more subtle benefits as a way to understand the system and what you can actually do to saturate the hardware beyond just having this memory pulse, right? The memory pulse is just a very easy way for people to understand intuition for what, but it lowers the latency of memory allocation. Of course, you control memory fragmentation. Of course, you can control the arenas, whether you're going to have a large pool arena versus a small pool arena. The default implementation uses a body allocator, which is a well-known concept if people want to look it up. But effectively, that's it's continuous recursively. It splits the memory in half, and it does left or right. And left is the pool of small objects, and so you have pools multiple arenas. You have the 16 kilobyte pool and the 2 megabyte pool, and this or that. And then largely, it allows you to make this upfront allocations. And so an example where we found some latency improvements is we've pre-allocate compressor blocks. So when you're compressing bytes, you need a place to temporarily stage objects. So this is another latency improvement and performance improvements that we've done. Well, if you've pre-allocated these objects at memory startup time, you've like, and you book it from the beginning of the memory pool or whatever. It turns out you never have to continuously make these large objects and put pressure on the memory allocator to give you these large objects to stage the writes for compression of these blocks. And so you allocate something large, and it actually gives you some meaningful performance improvements, right? Like single-digit percentages improvements for compression. So anyway, so there's a whole suite of reasons why it's beneficial. And I think if you're willing to go through the pain of building that, the downsides for people that are listening, there's like, okay, well, this sounds great. You get a bunch of performance benefits. You get like understandability of the system, right? It's all like pre-allocated up front, and you can either like basically the system either works or it crashes. And so that's a really useful high system, high level benefit of a system. The downsides, it's hard to program. Really, like the programmer has to be very intentional about programming against explicitly memory allocation API. And so anyway, so it gets a little bit of getting used to. It's never been, I guess, being 6 years operating and hire engineers, to date, it hasn't been a bottleneck for people to be productive with the code base, but it does get used to. It isn't something that is like immediately intuitive to people, especially if people come from managed memory languages like whatever, Python or JavaScript or things like that.
Yeah. That's very interesting. And I would love to read more about that. So if you have any resources, blogs, just send me over. I'll also attach to the description so people can visit that. Cool. You also mentioned the other benefit, or let's say where you kind of save some of the flushes when you have multiple requests within some short time frame. Because based on the protocol, you have a request and then you flush, you request and then you flush. But instead of that, you try to flush them together. What are the downsides of that approach? Like, are there any? Again, is it just the implementation? It's really specific. You have to do a lot of customizations there, or are there other problems?
Yeah. In this particular case, with the hyper-specific context of the memory allocator, that particular optimization was easy relative to the other optimizations. Like the things that I covered before, those were super hard. I would say like a harder thing to reason about when you're using a third code architecture and you're trying to tackle memory fragmentation is actually how do you parse the request of bytes? Right, it's not like integers can cross two byte boundaries of two different arenas. Like this is not how the memory allocator works. And so parsing of the bytes, there's a blog post that we wrote many years ago called an IO buff. And so we invented a data type to work around memory fragmentation. However, for this particular question, which is like when you're effectively skipping work, right? And so what we have to guarantee to the protocol is correctness, right? We cannot violate the correctness of Raft. And so, basically this has to be the same as this. And for people that are listening in the car on the drive to the office, I'm making hand gestures. Basically, that happens before hand gestures, right? So you have to guarantee from a protocol perspective that you're doing like, A and then B and then C, whatever the protocol mechanics are, right? Great. But I think people tend to conflate a synchronous protocol with communications. And so in other words, you can have a synchronous protocol where you say A and then B and then C. If between B and C, you can have suspension points so that other simultaneous execution of the protocol can be happening at the same time. So let me digest this a little further. So when you get multiple writes, it would be, they tend to be for different files on disk. Right? And so the NVMe SSD controller is going to flush full segments, typically a megabyte or so, like right, that's roughly what the segment size is. And so you get these benefits when you're doing a scatter gather style IO, where you're flushing you're flooding the physical parallel wires of the disk with as much information as the disk can handle in parallel. And then you coalesce, right? Like you insert some points of to like making sure that the protocol is continuing its execution of A, then B, then C, right? And so anyways, this optimization where like we're skipping high level work, right? Where if you're writing to a computer and you expect the writes to be durable, you can assume that we can accept, let's say, 3 writes at the same time for simplicity. From the like high level protocol perspective, we're still doing a write flush, write flush, write flush. But if you accept 3 parallel writes, you can issue the 3 writes wait for the writes to finish, right? Suspend. Remember, this is a coroutine implementation, so like you're going to wait, and so you can wait for the IO Reaper signal from whether it's IO Uring event to call back or using the AIO callback to tell the kernel, I was like, hey, your slot is ready to be reaped. You could be doing other useful work, like you can be decompressing the next set of network requests, etc. And so, but anyways, still on a single partition, you can make the write slightly larger, right? And so even though from a protocol perspective, you accepted 3 writes, you are doing at the mechanical level, you're actually making a larger buffer, and usually of the 3 writes. And so, but what it translates to, it's instead of doing write flush, write flush, write flush, you're doing write, write, write flush, and you skip 2 potentially expensive operations depending on the file system that you're using. So anyways, it's kind of a long-winded way of saying that other operations like fragmented memory parsing was hard. Teaching people to use this particular threading model was harder. This optimization was like relatively straightforward because we had already written the code, in a coroutine friendly manner, in a cooperative schedule manner. So we just simply suspended for 4 milliseconds. And then we waited for more work to arrive. And if work arrived within that coalescing window or that debounds window of the network buffer, of the network callback, then we would still issue the writes, and then we would fail them all or nothing. And so let's say the failure case is that the medium, the NVMe SSD device or whatever medium it is, could be S3. It doesn't matter, right? It's just an interface. If it fails, then you fail a batch of requests. So that was probably, I wouldn't say tricky. It was just sort of a matter of making sure that we didn't lie to the protocol for correctness. So those are, for that particular optimization, that was the only thing that we really over-index on. I was like, we have to make sure that whatever optimizations we make on the software, they don't change the correctness guarantees of the higher level protocols that we're relying for people to make sure that the data is safe. Does that make sense?
Yeah, that makes sense. Um, do you use like I don't know, formal methods or something to verify the correctness of the protocol? Or what has been your experience there? Like how useful in these scenarios it has been?
Yeah, so we hire a bunch of PhD people that really did their entire dissertations on storage work. The usefulness of using Raft is Raft was formally proven before we implemented it. And then it largely looks exactly the same. There's we haven't tweaked the protocol. And so in many ways, we're lucky that the protocols that we use had already been formally proven. The next set of tests is really where the rubber meets the road, which is making sure that our implementation matches the specification. And so for that, we use a bunch of tests, right? So we do a bunch of like fuzzy testing. We do where we like issue a bunch of like storage different requests, whether it's like, write, append, truncate, or whatever, like a series of operations. And then in memory, we know what the state should be, and then we issue the writes. we wait for the writes to happen, and then we verify that this gets that. We also inject failure modes based on like the Molly paper of failure injection. So we can like crash a node, we can insert an exception, we can sleep a particular thread, because sleeping in a coroutine implementation is free. All you do is you suspend the fiber. But there's like, it doesn't, it's fun. Like a particular code can handle millions of suspended fibers in memory. And so sleeping is super easy. And then we obviously do the Jepsen test, we do system tests, we do chaos tests, we sort of do, basically tens of hours of tests. I think right now it takes like 22 hours on the nightly test suite to run every night. I think it's probably creeping now to like 23, but last I checked was about 22 hours of just like a suite of chaos tests, of thousands of tests that we run against the system every night. And so anyways, but from a formal verification perspective, we are using protocols that had already been formalized.
Pretty impressive. Cool. We have talked about a lot of low-level details, and I'm sure, like as you mentioned before we started, like it can take like 6 hours because there's so much to talk about when it comes to performance and engineering that goes behind it. I want to kind of zoom out a little bit and try to understand the key architectural differences, like when we talk about like comparing traditional Kafka. From a very high level perspective, what are the key components and the key differences that add to the the power of Red Panda?
Yeah. Let me answer that question and also give you a teaser of the future, of how I think about the future. So at a high level, a big difference is Red Panda is a single system, right? So you can think of it as a single file, largely. And in that way, we eliminated categorical complexities. It's true we eliminated Zookeeper, but we also eliminated the schema registry and the HTTP proxy and this thing called cruise control. It's all of embedded. And so when you actually start adding systems, it is easier for the engineer to reason about one system than 6 other systems, right? Like I think that's a big differentiation. 2 is what I wrote on the Red Panda 1 blog post that I'll post on the link on the show notes here for the rest of the audience that wanted to follow up, is this idea of having one engine to span the latency spectrum from like ultra low latency, like this sporting events. Ultra low latency is always caveats because somebody from high frequency trading is going to call out. It's like ultra low latency right now is 800 nanoseconds. As I'm talking about 800 microseconds style latency. So for the space of application of space, this feels ultra low latency. All the way to multi-second writes, object and storage. And the reason why I think you can have that is that Red Panda, different from a database, doesn't have to do a lot of the very sophisticated index mechanics that databases have to do, right? So like if you profile a database, an inordinate amount of code and time is on the indexing code. Like, how am I going to keep enough memory metadata to be able to read, when you say select from people where ID equals 42, like how does that translate into the on-disk format, the multi-tier files on disk, et cetera, et cetera. We only do that for 2 indexes, the time index and the offset index. And it's otherwise a relatively straightforward implementation. It is, I think what is challenging here, and it's always a relatively straightforward implementation. What is challenging is to do it well across the latency spectrum because the mechanics are different. And you've built in assumptions in the code. There's that. And so I think a big difference for people thinking about Red Panda versus others is that Red Panda is a single file, if you think about it, a single engine that can span the latency spectrum from microseconds all the way to multi-seconds. And from a cost perspective, it's super cost effective, definitely on the control plane, on the operational layer. And then we've written code to offset things to tiered stores for many years now, right? So I think the part that is missing for us is to not touch disks, so you can deliver even farther savings. So it's effectively a layers on top of S3, like a write-through cache on top of S3. And so we'll get there soon. And so that's I think that's a big meaningful way of thinking about the world differently. And then from a platform perspective, I think we've continued to optimize that. And so I bought a company last year that did connectivity. And so when you're looking at like a platform for supporting these data intensive applications, it isn't enough to have a cost effective thing like Red Panda, or to have like a low latency thing, or a thing that integrates with the schemas. You sort of need, where the rubber meets the road is integration, actually fetching data from Oracle and putting it into Red Panda, or doing change data capture and putting it into Red Panda, or uploading data into S3. And so I bought the one of the largest connectivity companies in the world for that. We have about 300 connectors. And so anyways, as people think about the world and they're thinking about their Kafka needs, effectively, if you have any Kafka API, it works already with Red Panda. Super easy to use. So I'm biased, but it feels like the easiest way to get started. And then philosophically, it is a single engine that spans the latency spectrum from literally being embedded on space devices on a fraction of a core to, you know, the world's largest workloads on the Kafka, like today, that are happening. And I think soon we'll also have the write through cache through object storage too. So you don't have to like have many systems or many deployments to reason about it. You can simply let the application team choose the latency spectrum, and obviously, you know, that has like relations on the infrastructure cost. Lower latency will be slightly higher than object write through cache storage systems.
Okay, sounds good. You already covered like some of the key points about the future, but talking a little bit more about the future, like what's coming up in Red Panda, um, if you can share.
Yeah. My hope is that I think, and I've been part of the problem too, so I think I'll be the first to admit here. No one cares about between batch and real time. What people care about, like application developers, maybe infrastructure nerds do care about, but largely the world doesn't care. What they care about is they're trying to get their job done. And so I hope that this is the year where people stop thinking about it. And the reason is we released Apache Iceberg integration last year. More releases coming pretty soon, where now you're going to be able to write your data into Red Panda and it automatically appears query ready. And so like literally within seconds of the data appearing in Red Panda, you can issue a SQL query, but not with our query engine, whatever is your favorite query engine. So I think that is the keystone that will eliminate the need for people to battle, whether it's like, you know, real time or not. I think hopefully we'll move into this data intensive world. And then the second thing is how we're seeing people use us for this, you know, buzzword called like agentic workloads. And the idea, like what does agentic think? I think there was a researcher at Microsoft that put a pretty succinct description of it. Where he says like an agent is simply an object with a callback that is an LLM. And so in this world, you need the mechanics that led to the invention of Kafka, or a thing that looks like Red Panda, where you do with producers and consumers, you have, you know, policy enforcement, access controls, all that are needing to are remain true for these agents where you're like deploying them separately. And so I think what we are seeing today is Red Panda being used more and more towards this place where people are trying to build autonomy into their applications. And so if you think about a vertical slice, we talked about this late last year in our Red Panda user conference online, where we gave a view. I was like, hey, we didn't invent this. Like our users are using this in practice. We're just telling the story of how people are using the code. Was that you're going to have this operational layer that is going to automatically glue to your analytical layers via Iceberg. And then that in turn is also going to be glued with connectors, for example, to your autonomy layer. And so that's what I see the future being different, where I think every app is going to have some sort of intelligence. And I think Red Panda is going to be a small part of it, probably the center of it. And that's how I see the world. It's hopefully we stop talking about, you know, batch versus real time, and I think and start focusing on higher level problems. And I'm excited to be part of that future.
Awesome. Well, there are like hundreds of more questions that I could ask you in different areas, like low level, high level. But in the interest of time, I think I need to end this amazing conversation here. But probably we can talk more in further episodes when we get a chance. But yeah, thanks a lot for joining me and sharing all the amazing insights. I'm pretty sure our viewers and listeners are going to learn a lot. At least get some pointers into where they can learn more into performance optimizations, low level or high level, and they would get motivated to write something from scratch. So
Yeah.
thanks again.
Yeah, only advice is to go do it. It's fun. At least people will learn a lot.